In this video, we're going to look at protein denaturation. Now, in the previous video, we saw that proteins are just marginally stable, which means that we can easily denature them under certain conditions. So one way we can denature proteins is through temperature, that is, raising the temperature, or there is a way to freeze the temperature or lower it enough that proteins will also unfold. Now, we're just going to talk about raising temperature though. And so when you raise the temperature, you are giving atoms more motion, and with that more motion, you're more likely to come unfolded. Think about delta G equals delta H minus T delta S. An unfolded protein has a lot of entropy, so temperature will be modifying that entropy value. And proteins will melt or unfold cooperatively. What that means is that as one part of the protein starts to unravel, it will be like a domino effect. All of the proteins will unravel after that. And proteins will unfold much lower than 100 degrees centigrade. So it's easier to melt a protein than it is to boil water. pH will also cause a protein to unfold. Each protein is designed to stay in a specific pH range. However, if you put that protein in a different pH range, you can alter the ionization states of amino acids, and we've seen this already in this course. And when you change the ionization state, you can break hydrogen bonds or break ion pairs, which means the protein will unfold. Detergents can also unfold a protein because a detergent is made out of a nonpolar part and a polar part. Think of a lipid. The detergents look like lipids. And so they will associate with the nonpolar portions of the protein, which are on the inside, and this will cause the protein to unfold now that you no longer have that nice, tight, hydrophobic core. And you can also use chaotropic agents to unfold a protein. Such agents are guanidinium or urea. Now, it's not quite known how these things actually work in solution, but the idea is that for some reason they increase the solubility of nonpolar substances in water. And usually if you have 5 to 10 molar of urea or guanidinium, your protein will unfold. Now, there was an experiment roughly 60 years ago now by Anfinsen that showed that it is possible for some proteins, once they're denatured, to become renatured. Now, not all proteins can do this. Think of eggs. When you fry an egg, you're actually changing the proteins in the eggs. And once you fry an egg, you can't unfry it. You can't renature those proteins. Well, in 1957, Anfinsen was looking at the protein ribonuclease A. And in its native state, ribonuclease A has disulfide bonds. Well, he added 8 molar urea and broke the disulfide bonds with 2 mercaptan ethanol, which unfolded the protein. And what he saw was when he removed urea and he removed the new 2 mercaptan ethanol and allowed the protein to reform, it reformed in its native conformation. It was still active. And the probability of this happening by chance was 1 out of 105. And that number comes from the disulfide bonds reforming correctly. They can reform incorrectly 104 ways and only reform correctly 1 way. And he saw that the majority of the proteins reformed the correct way. And the big takeaway from this, and what is true about proteins, is that the primary structure of a protein will dictate what it looks in 3 dimensions. So primary structure dictates secondary, tertiary, and quaternary structure. Oops. Let me go back here. And when we think about proteins, though, I don't want you to just picture a molecule that really doesn't move. Proteins are constantly breathing. They're not rigid. So what you're seeing here is a computer simulation of what the inside of an E. coli might look like. Each one of these blobs is actually a protein, and this blob or this string of beads right here is a unfolded protein. And what you can see for these proteins, if you look at any color, they are constantly moving, and that is true of proteins inside the cell. They aren't static, they are constantly moving, or as we say, they're breathing. So on average, a protein can change its conformation by 2 angstroms just by random motion. And a protein can actually have multiple stable conformations. And the change in this conformation, it can be due to outside influences such as putting in different pH, or as we'll see with hemoglobin later on in this course, if you bind a ligand, that binding can provide enough energy to cause one of these changes in states. Now, not all proteins have a distinct three-dimensional structure. Some are always going to be disordered. That is, their structure is rapidly changing and never defined. We call these proteins intrinsically disordered proteins, or IDPs. Now, IDPs, a lot of the times they have many charged amino acids. For example, an IDP might have a lot of aspartic and glutamic acids, and that will prevent folding because all the negative charges will repel each other. Or they could lack hydrophobic groups, so you can't form that nice hydrophobic core. In fact, half of all eukaryotic proteins have long IDP segments, and intrinsically, when you look at prokaryotic proteins, they generally don't have IDP segments. Now, IDPs, we'll see this later in the course too, can be associated with some diseases. And they also can be used to signal and for regulations. So here is one example of an IDP that is disordered, but once it binds to another protein, it forms into a helix conformation, right? So IDPs are signaling regulation, while ordered proteins, things that do have 3D shapes, we generally think of those as enzymes, as transporters, or as structural components. And that is it for this video. I will see you in the next video.